Chapter 11, we're looking at thermodynamics. And we said in the last chapter both heat and work can change the internal energy of a substance. If we don't change the phase of that substance, its internal energy is proportional to its temperature. For example, if we pull a nail out of a piece of wood, if we do it quickly, and then we feel the nail's going to feel hot. We did work on the nail, and that work translates into an increase in the internal energy of the nail, and that manifests as the nail warming up, feeling hot. In thermodynamics, we're going to be working with two parts of our universe. We're going to be working first with the system, and we're going to define the system as the substances of interest, the container, the mechanism that's going on, and it has a clearly defined boundary. The environment then is everything else, the surroundings, and the surroundings that can affect the system. The system can also affect the surroundings. For Chapter 11, for looking at thermodynamics, we're going to focus on the energy changes due to work and heat on gas in a cylinder. So we're focusing on gas in a piston cylinder or in a refrigeration tube cylinder. And we're going to be working a lot with pressure volume graphs. So pressure on the vertical axis, volume on the horizontal axis. And when I take pressure times volume, it turns out the area under the curve is work. How do we get that? Well, we start out with an equation that should look familiar. Work equals force times distance, force parallel times distance. We're going to just multiply that by 1. And 1 is in the form of the area divided by the area, surface area. So we can rearrange this now to say work equals force over area times distance times area. We learned in the last chapter that force over area equals pressure. If we're talking about a cylinder, our area is the surface area. Our distance is the height. The surface area won't change in a cylinder, but if I have a piston in a cylinder, this height can change. So I have pressure times the change in volume, because it's the volume of a cylinder. Work equals pressure times change in volume. And we often refer to work in this area as P delta V work, as opposed to F times D work. Okay, let's take a look at an example using this new equation. We have a cross-sectional area of a cylinder that's 0.01 meters squared. We want to find out how much work can be done by the gas if it exerts a constant pressure and moves the piston a particular distance. So let's work through this. Okay, our change in volume is going to be our cross-sectional area. It's a 0.010 meters squared times our change in distance, 0.040 meters. So our change in volume is 4 times 10 to the negative 4th meters cubed. Pressure is constant, so work is going to be P delta V. Pressure is 7.5 times 10 to the 5th pascals. Just found our volume change, 4.0 times 10 to the negative 4. So we end up with 300 joules. It says work is done by a gas. The gas is expanding the size of the cylinder, so it's pushing the piston out. We end up with a positive number, and what we're going to find is that when work is positive, it's done by the gas. Conversely, what we're going to find is if we end up with a value for work that is negative, we're going to have work done on the gas. So we've got two quantities, work and Q, heat, and both can be positive or negative. So that's something we need to keep straight. Both of those quantities lead us to the first law of thermodynamics. First law of thermodynamics says that the change in internal energy, or delta U, equals Q, or the heat, into or out of the system, minus the work done on or by the system. You can also see this equation written as delta U equals Q plus W. They're the same thing. What you need to do is just keep track of what is the sign for Q, what is the sign for W, and that will help you figure out what happens to the internal energy. So just to review, if heat is positive, heat is added. If heat or Q is negative, heat is removed. And that's added to or removed from the system. Work, if work is positive, it is work done by the system. If work is negative, it is work done on the system. Mnemonics, if you want, heat is added, that's plus, removed is minus. For work, it's a little harder. On and negative both have ends. That might help you. So let's take a look at a problem that uses that information. So we have a total of 135 joules of work is done on a refrigerant as it undergoes compression. So if it's done on, that means that my work is going to be negative. If the internal energy increases during the process, what is the amount of energy transferred by heat? So we're looking for Q. So we'll start with our equation, delta U equals Q minus W. Our internal energy change is positive, so we have a positive 114 joules equals Q minus work is done on the gas, so it's minus negative 135. So we take 114, and this is going to be Q plus 135 if we just do the next step. So now we have to subtract 135 from each side. We end up with negative 21 joules equals Q. So the question now asks is, has energy been added or removed to the refrigerant by heat? Well, we take a look at our sign. Q is negative, so heat has been removed. When we are working with pressure temperature graphs, we have three different processes that we can consider because we have a variety of different things that can either be held constant or that can vary. We're going to start out with something called an isochoric process. For an isochoric process, we have a constant volume. When we have a constant volume, delta U equals Q, the heat, because work equals 0. Why does work equal 0? Well, if delta V equals 0, work is P delta V, so no volume change means no work. No work means that the internal energy change is due to any heat added or removed. The graph for something like this is going to look like the one showed. So pressure here, volume here, constant volume means I have a vertical line. So again, constant volume is an isochoric process. Isothermal process, as hopefully you can figure out, thermal referring to temperature, iso, remember, means same, so isothermal process is a constant temperature. If you remember that internal energy change is related to temperature change, here we find that the internal energy change is 0. And the internal energy change is 0 because the temperature is constant. So what we have now is that work is equal to heat flow. So if I add heat to the gas will do work and cause the volume to increase. When I have an isothermal process, I have a curved line on my graph, and so the temperature along the curve is the same. We're going to be looking at processes that involve changes between isochoric, isothermal, and the next one, and so we'll be able to recognize those parts of the process by looking at the shape of the line on our pressure volume graph. The last process we're going to talk about is something called an adiabatic process. An adiabatic process has no heat transferred, so delta Q is 0. What that means then is that the change in internal energy is equal to negative W. What the heck does that mean? Well, if we think about this, if you pump up your bicycle tire and you do it rather rapidly and then you feel the barrel of your bicycle pump, if you're doing it by hand, the barrel will feel warm. Okay, you didn't add any heat to the barrel, but because you were doing work by continually and rapidly compressing the gas, what you did is you increased the internal energy of that gas, and that again was manifested by the temperature going up. So that would be an example of an adiabatic process. Another example would be if you've ever used an aerosol can and you've emptied it all at once and then you feel the can should feel cool. Again, you're causing gas to expand, so the gas is doing work on the environment, spreading out, pushing air out of the way. So it's doing work, it is giving up its internal energy, which means its temperature is dropping. So let's take a look at an example. Here's a graph that represents pressure volume change, and we have a cycle going on. We have 3 different points, and we'll take a look at how does the value of work for the process AB, so it's following path 1, compared to the same process if I follow path 2. Path 2 is 2 sides of a right triangle. How do we figure that out? Well, let's take a look. We'll start out with path 1, so we're going from A to B this way. So we have constant pressure, and our pressure is 1.5 times 10 to the 5th pascals. Our change in volume is final minus initial, so it's 30 minus 10 times 10 to the negative 3 meters cubed. So work is just going to be P delta V. Multiply those two together, and I get 3,000 joules. Now, the gas is getting bigger volume-wise. Since work is done by the gas, it's going to be positive. So work is the area under the curve. So there's the amount of work done going from A to B along path 1. Let's look at path 2. If we go from D to B, first of all, work equals 0. The work equals 0 because my change in volume equals 0. So now I'm going to look at the work from A to D. Work is area under the curve. So there's my area under the curve. It's a trapezoid. So I have to remember how to do the area of a trapezoid. So it's 1/2. Base 1 times base 2, that's a change in pressure. So I have 1.5 plus 0.0 plus 0.7 times 10 to the 5th pascals. And then my change in volume is final minus initial. Again, volume's increasing. 30 minus 10 times 10 to the minus 3. So again, my volume's increasing, so the gas is doing work on the system. I do the math. I get 2,200 joules. Since the gas is expanding, it's doing work on the system, so I get a positive 2,200 joules. So depending on which path I take, the work varies. So it turns out that work depends on a variety of things. Work depends on initial and final conditions. And, more importantly, sometimes, work depends on the path taken.